common conundrum about gravitational waves is that if they bend and stretch space-time itself, how are we supposed to measure this deformation? Wouldn't my ruler also get stretched? Let's start by describing the detector used in the LIGO experiment. It is a giant interferometer with an arm length of 4 kilometers. Within the arms, there are Fabry-Perot interferometers that bounce light in between them, which makes the light go even further than those 4 kilometers. After splitting, the two light beams meet again, and depending on their relative phase, we can measure interference. If everything is perfectly still, we measure a certain interference pattern. But if something happens to the light waves between splitting and interfering, we get a different interference pattern. Now, how do gravitational waves get involved? We have to make sure that gravitational waves change something along the light's path. To do this, the mirrors at the end of the interferometer get mounted like a pendulum, so they can move almost freely. If a gravitational wave hits them, they feel a force pushing them in a certain direction, and since there are no interatomic binding forces etc. holding them at rest, they follow this motion. If the mirrors were mounted using a solid construction, the binding forces of this construction would act against the force of the gravitational wave and the mirror wouldn't move. But if space itself is stretched along a gravitational wave, isn't the light's wavelength also affected, which would make the interference pattern stay the same? This is true, but those two processes happen at completely different timescales. From the light's point of view, the oscillations of a gravitational wave are extremely slow. This means that we can clearly distinguish interference patterns that happen before, during, and after the gravitational wave hits. During the stretching of the interferometer arm, yes, the propagating light's wavelength gets stretched too, but we just ignore those light waves. Instead, we focus on the different interference patterns before and after the wave. After the gravitational wave has passed, the mirrors are still moving and light propagates with the same wavelength as before. That's why we see a different interference pattern and can deduce that a gravitational wave has passed by. By the way, you need extremely high accuracy in order to measure this. It's like measuring the circumference of the Earth with the precision of a few atomic nuclei. That's pretty much it for this time. Thanks for watching and see you next week.